welcome to the webinar Optimize the Signal Acquisition for Optical Measurements. My name is Kirsten Sonnabend. I'm Associate Editor of the journal Physik Journal, and I am your moderator of today's webinar. Our speaker is Dr. Claudius Rieck. He is an application scientist responsible for all photonics applications at Zurich Instruments. With 7 years of experience in ultra-fast photonics, in particular terahertz time-domain spectroscopy, laser scanning microscopy, and frequency combs, Claudius is curious to look into new applications way beyond optics and photonics. I would like to take this opportunity to welcome Claudius. Before we start, I would like to give you a few hints on the course of the webinar. You should now see the title page of the presentation on your screen. This is an interactive webinar, which means that you can ask questions at any time during the presentation. Please use the small window below the actual presentation window. The presentation will take about 40 minutes. Afterwards, Claudius Rieck will answer your questions. If your specific question cannot be considered in the discussion, the experts from Zurich Instruments will answer you by email after the webinar. One more note on behalf of ourselves. This webinar will be recorded and then made available on our website prophysik.de as an on-demand webinar. All registered participants will be informed by email as soon as the recording is available. And with that, I now hand over to Claudius and look forward to his presentation.
Thank you for the kind introduction, Ms. Sonnabend. Let's jump right into it. What can you expect in the next hour? In short, we will show you how to optimize signal-to-noise ratio and therefore save precious measurement time. We will do that by addressing questions like, why do we actually need signal recovery for optical signals? We will have a look at photonics measurement setup in particular, and we will have a look what are the noise sources which affect the measurements. We will show you how lock-in amplifiers work in Boxcar Averagers and how they can overcome noise and suppress the noise. So, in addition, we will show you how to effectively use lock-in amplifiers and Boxcar Averagers. We'll do that in 3 case studies: tunable diode laser absorption spectroscopy, as well as pump probe measurements, and as one particular example, stimulated Raman scattering microscopy. But let me briefly tell you a little bit about Zurich Instruments. At Zurich Instruments, we have a clear mission. We want to provide the best-in-class dynamical signal instruments for advanced R&D labs. Now, how do we do that? We do that by using high-performance hardware with highest sensitivity, low noise, and high resolution. But we don't do our own chip designs. What we take would already exist, but what we add is our outstanding software. We add the FPGA code running on the devices itself. We add our user interface and the APIs, which is very rich of functionality and features, and therefore allow a very efficient workflow and save you time in implementing and performing your measurement needed. This led to 4 measurement categories. We have lock-in amplifiers, Boxcar Averagers, impedance analyzers, and arbitrary waveform generators. Later, we combine with our measurement technology to our quantum computing control system, the QCCS. But today, we will concentrate and focus on the lock-in amplifiers and the Boxcar Averagers. Now, let's go back to the actual experiments we want to look at. These are optical experiments. The question is, why do we need signal recovery for them at all? Now, optical measurements have one real benefit. They can make measurements of highest precisions. I choose two examples here. One you will immediately recognize. This is the LIGO experiment, where you can measure distances with a precision of down to 10 to the minus 21. And the other one is an ultra short laser pulse measured in amplitude and phase with temporal resolution in the attosecond timescale. Now, there is only one caveat with optical signals. You cannot directly record and capture the photons. You have to convert the optical into an electronic signal while preserving all the information content. And let's have a look how this is typically done. Therefore, let's look at a few typical optical experiments. Here on the top you can see spectroscopy setup, terahertz time domain setup, pump probe as well. Now, all of those we can combine, we can consist of 4 functional sections. We will always have a source shown in dark blue. We will always have an experiment. There will be a detector actually transferring the photons into electrons, and in the end we have the signal analysis. In general, here we want to focus on spectral integrating sensors like, for example, photodiodes, PMTs are on, but we want to concentrate on the signal analysis, because the sources can be very different, the experiments can be very different, and we don't want to go into the detail there. But the signals will always look very similar. For example, like this. So we have a parameter variation which leads to a time-dependent signal. And what we want to optimize in the very end is the signal-to-noise ratio. So signal-to-noise ratio we can define like the signal, the mean signal measured here, for example, on this plateau, being something like 1.4 millivolt, and the noise, which is quite typically the standard deviation over several measurements. Now, to optimize the signal-to-noise ratio, it's fairly straightforward. Either you want to capture all signal components, so you want to maximize the signal, or you want to minimize the noise, so you want to suppress the noise by, for example, averaging. But before you can suppress the noise, it's very important to understand what are the noise components which affect your measurement. Therefore, let's look at a very typical noise floor. So here we have we depict the power spectral density measured over a wide frequency range, and we can identify 3 typical noise components. We have the 1 over F noise depicted here. We have the white noise floor, which is constant over the whole frequency range, and we have a few individual noise peaks, which, for example, come from the source itself or come from pickup, like whatever, radio signals or the typical 50 or 60 hertz power line pickup. Now, what you can see immediately, if you want to measure a signal at DC, so 0 frequency, if you kind of just switch on your signal and then you average, this means you would filter with a low pass filter here at the DC. But here, the noise which you would acquire, shaded in blue, is huge compared to the signal. Now, what we actually want to do, we want to measure in the regime over here where we have only a small noise contribution. And this we can do by adding a modulation. We therefore shift the signal by modulating the photon beam after the source or in the experiment actually, and we can analyze the signal afterwards with a lock-in method. By choosing the best modulation frequency, we can kind of select where we want to measure. In this case, obviously, frequency 2 with the lowest noise would be most beneficial. We want to select the best modulation method depending on the frequency range which we want to look at, and there I selected kind of 4 typical methods. First of all, the very well-known chopper wheel. This is really a mechanical chopper, interrupting the laser beam, and we can achieve frequencies in the range of few hertz or up to the tens of kilohertz machine. We have an acoustic optic modulator, which is based on inducing refractive index grating into a quartz crystal where the laser beam will pass. There we can achieve higher frequencies, and we can kind of go to even higher frequencies with electro-optic modulators or Optical cells, which work with an electro-optic active material in between two polarizers, and there we can really achieve frequencies up to several tens of gigahertz. For example, telecommunication uses EOMs a lot. But there is an additional possibility. We can also use a modulated laser, so we modulate the pump power of the laser, or we use mode locked laser itself. There we can also go up to frequencies of 10 gigahertz. Now, what you need to do as well is you need to choose the right lock-in amplifier which matches the input bandwidth. And this is the first and only point where I will show the portfolio. We have the MFLI covering more the lower frequency parts up to 5 megahertz. We have the HF2LI covering everything up to 50 megahertz. But if you want to go really to the fastest processes, or for example video rate imaging, you would like to go to even higher input bandwidth and measurement bandwidth, and this would be then the UHFLI. But now let's look in more detail how lock-in amplifiers actually work. I already mentioned we need to have a modulated input signal. This is what you see depicted here in light blue, and you also see the modulation under there. This will be multiplied in the mixer over here with the reference signal, which can be either generated by the lock-in itself or come from the outside, so a sine wave. The output of the mixer is sent through a low-pass filter, and we will get as a result the amplitude and the phase. Now, excuse me, what you can do, you can change 3 parameters typically in the lock-in amplifier. First of all, you can change your modulation frequency and select the range where you want to measure. You can change the cutoff frequency of your low-pass filter, and you can change the filter order. Now, let's have a closer look at the filter bandwidth and the filter order. What do they do and how do they affect the signal? So, first of all, let's look at the filter bandwidth. On the top left, we see a step response, and we see what a filter order with a particular bandwidth, how this filter smears out the step response. And we see the more narrow the bandwidth, the more smeared out the step response is. So the less precise in time your signal will be. At the same time, we see that the frequency response gets more narrow, and as we remember, if the frequency response gets more narrow, we will collect less noise. The filter order defines how steep the filter is, so how well the cutoff is in the frequency domain. We see kind of the lower order filter has a very shallow slope, and the higher we go up in the order, the steeper it goes. Now the effect in the time domain, so again as the response onto this step signal, we will see that the smearing out occurs in a different way. And in the end, these are 2 parameters which we can use to optimize the signal. For example, if we want to have an immediate rise of the signal, we may want to use a lower order filter, first order for example. But if we have some noise spike close by, we might want to use a higher order filter. We will see that also later in the demonstration. So let's jump to the first demo, tunable diode laser spectroscopy. There we scan a laser over a certain frequency range by adding a sawtooth signal to the laser controller. On top of that, we add a modulation signal with the MFLI. The laser photons are partially absorbed by the gas atoms depending on the concentration, and the residual photons are captured by a photodetector, and the signal is analyzed afterwards with the MFLI. The MFLI will depict the signal over time, and we don't have an actual laser setup here, but we have an external source which provides signal which represents the laser signal. So I will move to the user interface of our device. So here we go. The user interface runs in a browser. In a browser window, we can maximize this. On the upper part, you see the lock-in amplifier. So here you see the control of the signal input, you see the reference signal, you see the mixer and the low-pass filter, which we discussed. All of that is, of course, implemented in a digital way, so that we can very easily transfer the data afterwards to the computer. Now, to start a measurement, as I mentioned, it's of paramount importance to know the noise floor of your signal. Therefore, we start the sweeper integrated in the setup. We select the noise amplitude sweep, and I would suggest let's perform a measurement somewhere from 800 Hertz to 1 megahertz. We select the reverse way and we start the measurement. Now, what you can see, the noise signal per square root hertz is depicted over the frequency range, and we see that there are some noise peaks. They get much higher the lower we go, but the baseline is somewhere on the order of 5 nanovolts per square root hertz. Now, here at something like 10 kilohertz, we see the set-in of the 1 over F noise. So on the right hand side, so the higher frequencies, we have pretty much a white noise floor, and now we have a wide over F noise, but we also have certain spikes in the signal. You can see that the measurement finished now, and we can clearly say, okay, we might want to stay in the regime, let's say a little bit above 10 kilohertz or above. Now, what I would like to do. Now, first of all, I select the measurement frequency, so something like 2 kilohertz, and we need to select a fairly high measurement bandwidth at the beginning. Let's take something like 300 hertz. We'll optimize that in a minute. Now, what the measurement setup will do, it will send out a trigger every time we start a new frequency sweep. And based on that sweep, we will start to acquire the data coming from the MFLI, from the lock-in amplifier, and depict that over time. So we will always do triggered measurements. Now I start the actual signal. So here we go. Okay, we start the actual signal. Maybe as a very first step, let's have a quick look at the signal with our scope. You will see on the left hand side, I select the scope, pull this over, and this is integrated, and I can just quickly run and check if we see some of the signal. So we see some modulation, but it seems to be a very small signal. what it actually is, because it is highly attenuated to make it realistic. But there is something which we can try to log onto, and this is what we'll do now. So I start the data acquisition again, run a single measurement, and what we see is our kind of 1, 2, 3, 4 peaks depicted over time here, which represents the actual wavelength change. Now, what we see is that there is some ringing on top of the pedestal, so to say, and the peaks look a little bit asymmetric. Now, the asymmetry is quite often an indicator that the actual low-pass filter corroborates the signal. So I will kind of acquire one measurement after the other. We will limit, in the history, can limit the number of samples, traces, which we display, and then we can try to optimize the settings here. So if the filter smears out the features, this would mean the bandwidth is a little bit smaller. So we have to increase the bandwidth, let's say, to something like 600 kilohertz. But now we see that the noise also got higher. If the noise gets higher, let's quickly go back to the sweeper. So here we see clearly a strong noise peak at 1 kilohertz. We are located at 2 kilohertz at the moment, so I would guess with 600 hertz we will still have this guy leaking in, what we want to avoid. So we can push that further out or change the filter order. Let's first change the filter order, so you can immediately see the effect. I stop the measurement and make a clear comparison. So I run one trace at the actual setting. Then I will change the filter order and adapt the filter bandwidth. Excuse me. And run a second measurement for comparison. And as you can see, we were already able to suppress this residual part a little bit, but not good enough. So next thing, what we need to do, let's push out the frequency further, for example, to 10 kilohertz, and perform another measurement. And what you see is the result looks way better. The signal looks really nice and calm, and we can further optimize the filter settings. I go into the run mode again, and maybe we can open up the filter a little bit more and see, the features are even more narrow. So we go something like 2 kilohertz or 3 kilohertz. Even 3 kilohertz made a difference, but we have again leaking. Now we can enhance it further. This doesn't change the whole game, but maybe we want to adapt the frequency. Let's go to something like 100 kilohertz. And as you can see, now again the signal became a little bit calmer. And what you can see now as well is if we increase the bandwidth now, the shape of the features stays precisely the same, but we have an increase in the noise level. And so therefore, what we do, we can, for example, also zoom into the Y scale. We zoom into the Y scale and use two markers. Calculate the mean and standard deviation in the markers, and optimize the bandwidth now. Go down again to something like 1 kilohertz, and the standard deviation is on the order of now below 200 nanovolts. I think we could even better, but now we see again a smearing of the smearing out of the features. So this is what we of course have to provide, because it could affect the measurement. So let's go back to something like 1 kilohertz, what I think is a really good compromise to the settings in the very beginning. And what we can even try in addition is going maybe to even higher frequencies. I will try to go to 3.4 megahertz, for example. And what we see also here, we got an additional increase in the signal-to-noise ratio. So let me jump back to my PowerPoint presentation and recap. The take-home message here is clearly spectroscopy measurement needs to have 4 steps. First of all, you need to characterize the noise floor, ideally with the device you want to use to measure later, for example, a lock-in with a sweeper built in. You select the best modulation frequency where you're in the lowest noise regime. Afterwards, you optimize your filter bandwidth and the filter order so that when you perform your measurement, you can see all the features in the signal which you're interested in. Now, this was a typical representative of spectroscopy measurement. There is another very big family which we would like to address now. These are pump probe measurements. So in pump probe measurements, we have typically 2 or even more laser pulses, the pump pulse and the probe pulse. They are separated by, for example, a beam splitter. One of them typically the pump goes over a delay line, and therefore we can adjust the delay between the pump pulse and the probe pulse. Impinging on the actual sample, the pump pulse will induce a certain change in the sample, for example, transmission change or refractive index change. This change is probed later on by the probe pulse when arriving a little bit delayed, depending on the delay line. And afterwards, we analyze the probe pulse strain and measure the actual interaction. The great advantage of all pump probe techniques is that the temporal resolution is not given by the measurement gear, but by the laser pulses themselves. And this is how we can achieve measurement durations as short as picoseconds, femtoseconds, or even attoseconds nowadays. Now, there is a huge variety of different pump probe related techniques. As 3 representatives, the first one is kind of a classical pump probe with a visible pump and a near-infrared probe where the transmittance of a certain molecule material is measured. The next one is terahertz time domain spectroscopy, where the probe experience a refractive index change of the co-propagating middle infrared or far infrared field, and therefore we can sample the electric light field of an ultra short pulse point by point and completely recover this in amplitude and phase. In addition, we have the subfamily of nonlinear microscopy like CARS, SRS, 2-photon or 2-photon, 3-photon multi-photon microscopy, which also relies heavily on short pulses and measuring at kind of pixel by pixel the signal of the pulses. Now, if we want to look at this kind of signal, we can see the signal is confined very, very tight in a short pulse. Therefore, it's a periodic signal, but it's for sure no longer sinusoidal. Now, this has the consequence that the signal is not only very confined in time, but also spread out in frequency. And if we apply a lock-in amplifier on that signal, what we can do, we will only capture one harmonic, the fundamental. Now, to do it in a better way, we want to look now at the Boxcar Averager principle. It's kind of obvious what you need to do. You only need to measure during the time with the relevant signal. So we can add a Boxcar window, which is kind of 1 during the time when we measure and 0 otherwise. Now, the smaller the duty cycle, the more we now also span out in frequency, and we see the envelope of this, it's a zinc filter, and this envelope is directly proportional to the filter, to the boxcar window width. And if we make the window very narrow, then we span out in frequency. We collect the signals of all those additional harmonics, and therefore we can gain in signal-to-noise ratio. What I want to say here as well is, of course, we do not only measure signal there, but noise. But remember, typically at low frequencies we had the 1/f noise coming in, and at high frequencies we have the white noise, and the further the further the signal is spread into the regime where we have only white noise, so a very low noise floor, the boxcar can really bring a big benefit for the signal to noise if he can measure over there. Now let's have a look at a particular example. Now, how do we have to set up the setup? So again, we have our pump probe measurement, and in this case we will choose it in a way that the pump imprints a signal on every second probe pulse. So we really have one pulse train which carries the signal, and the other pulse train which doesn't carry the signal. We average over several n of those periods. Signal on and signal off on a probe is one period. This is the repetition rate, so to say. And we want to capture now the signal point by point. Therefore, we want to do more than only doing a boxcar. We can clearly say also a lock-in can do the measurement. So the lock-in will be locked at the modulation frequency of the pump pulse. So kind of every other pulse is captured at the maximum of the sine signal, and the other pulse train is suppressed. We still capture only the fundamental harmonic, but we can do the measurement. Now, if we add the boxcar, we will do now two things. We add a boxcar with a so-called baseline suppression. What does that mean? This means we have one boxcar window being positive on the signal, and we have another boxcar window on the pulse which does not carry the signal, so we integrate over this as well, but we subtract this signal. As a consequence, in the frequency domain, we average the signal, we collect the signal at all odd harmonics, and what is even more important, so one beneficial part of the baseline suppression is we suppress all the C components. That's where also the name came from. So let's have a look how this looks at an actual signal if we implement it. We use for demonstration our UHFLI lock-in amplifier and Boxcar Averager, and I will share my screen with you. So here we go. We maximize the window so that you can observe everything. We have on the top the lock-in section of our device featuring 8 demodulators and 8 oscillators. And the first thing which we can do, we can try to see some signal with the oscilloscope, which I started here on the bottom. And we can see we have an input signal of kind of 2 pulses. I can do that more often, and we will see that one of the pulses stays as it is and the other one changes. Now what we have as a trigger signal is the repetition of this signal. So we take the trigger 1, this is the input, and we lock one of the oscillators as an external reference to that. Since it's generated at 125 kilohertz, we also get the frequency of precisely 125 kilohertz. And this frequency we can use as an input parameter to one of the lock-ins, so one of the demodulators, where we analyze the actual signal with a certain bandwidth. Now, this is how you set up the lock-in measurement. Now we go, we want to set up the Boxcar. For the Boxcar, we have a tool called the PWA, because in this case, the signal is fairly big. And we can even see it basically without averaging. Sorry. So this is not a problem, but let's make it a little bit more interesting and attenuate the signal strongly by 40 dB. Then we see immediately that the signal is completely gone. Oh, no, there's still a little bit impinging sometimes here, but it's barely visible with the scope. With the Boxcar Averager and the PWA, the periodic waveform analyzer takes basically the periodicity of the signal, averages those, and we depict here the amplitude on the left-hand side over the phase of that repetition. This has a great advantage, even if your repetition changes, for example, because the cavity of your laser changes, or you have other reasons that the repetition frequency changes, the phase will automatically kind of adopt, because we follow the external reference, and therefore, for example, a zero crossing would be still, if you think about a sine wave, would be still at 180 degrees no matter what happens, and therefore you don't have a smearing out, for example, of the zero crossings. Now, let's use a periodic waveform analyzer to set our Boxcar windows. We have already here kind of two Boxcar windows defined. Now we don't see the signal. What we do, we can quickly add the number of averages, which we do, so 400,000 cycles, for example. And if we then start the measurement, we see immediately that we capture the signal. To make it a little bit less distracting, let me switch off the manual, the auto zoom mode, and pull the signal a little bit in the middle. Now, at the beginning, I would like to start with a slightly broader window. Therefore, we take those two cursors, we define it, and we copy the gate from the cursor window. You see a second window here on the right-hand side. This is our baseline window. The baseline window has always the same width than the Boxcar window, so that it kind of contains the same signal and the same noise. And we can either start it at a certain offset, so you choose 180 degrees because we have a perfect periodicity here, but you can also change it, for example, to a certain start phase, like whatever. Let's put it at 100 degrees. This is of course important if you have, for example, multiple probe pulses in your pump periodicity, and you want to subtract kind of the actual probe pulse carrying the signal and the directly succeeding pulse, because they will be on the shot-to-shot noise level be most similar, and therefore have the smallest difference, and can be used for averaging in the best way. But let's go back and putting the offset again to the 180 degrees, so we set the Boxcar window in a good way. The Boxcar bandwidth we define over the averaging periods, and we choose it in a way that we have the same averaging bandwidth than the lock-in. And now let's look at the result in our plotter. Here we depict the signal over time, and we start the measurement. What we see is we have the Boxcar depicted in green and the lock-in depicted in orange, and you can immediately see there is a big difference in the signal to noise ratio, although we have the very same averaging bandwidth. This is really due to the advantage of the Boxcar, and we can tweak that even a little bit by adapting slightly the width of the Boxcar windows. Let's try to make it a little bit more narrow, and please observe for me the signal in the plotter. First of all, I changed the width. Now I changed the starting point a little bit, so that we really capture precisely only the signal of interest. Maybe went a little too far now. And now let's go back and adapt the signal again. and what you can see, maybe I can make a quick jump, and you see the noise was more or less comparable, but now we have more signal on the actual scale. We could push it even slightly higher, and now I would say we have on the order of kind of 5 times more noise on the lock-in than on the Boxcar. This means the Boxcar has a signal-to-noise ratio advantage of factor of 5, and as a consequence, as you know, the measurement time goes with the square of the signal-to-noise ratio. You could measure with the Boxcar 5 to the power of 2, so 25 times faster. And depending on your whole signal setting, the noise floor, and your pulse, and your signal form in the end, this can go much higher, even up to 100 times faster measurement with the Boxcar compared to the lock-in. But even if the lock-in is almost optimized and we are basically at the shot noise limit, so in the white noise regime, we can gain typically a factor of at least a factor of 2 or more. I would like to summarize this and jump back to my slides. The clear take-home message here is the pump probe measurement with Boxcar and Lock-ins you also do in typically 5 steps. First of all, you lock one of the oscillators to your repetitive signal. This is used as a modulation input of the lock-in, and you set the filter bandwidth and the filter order accordingly for the lock-in. You identify the pulses with the PWA for the Boxcar Averager. Afterwards, you set the Boxcar windows and optimize their width and their starting point. And in the end, you perform the actual measurement, and you can then make the judgment which is the best technique for your actual signal which you want to analyze in this specific experiment. To show you that the Boxcar advantage is not something theoretically what we can only demonstrate with our instruments here, I would like to share with you the measurement of the stimulated Raman scattering microscopy. Here we precisely have this situation where we kind of have one pulse carrying the signal on the pump pulse train, and one not carrying the pulse, because the whole setup is based on a 40 megahertz oscillator where the pump has a full 40 megahertz, and the Stokes pulse train is pulse picked down to 20 megahertz. The whole experiment was taken the way that we took the data was taken for each pixel, and therefore we can now very well compare the pixel dwell time on images and measurements which basically show the very same signal to noise ratio. And you can see 2 examples on the right hand side. First of all, the one for the lock-in amplifier, which was able to detect a pixel dwell time of only 14 milliseconds on this super weak signal. But at the very same signal, the Boxcar was able to speed up the experiment, the measurement, by a factor of 2 without losing any signal-to-noise ratio. And I think this is a really great result, given the fact that the lock-in was already optimized to the frequency regime where there was the minimum amount of noise coming in. There was basically only white noise, and we were very close to the shot noise limit where the measurement was performed. And even there, the Boxcar Averager could have an improvement in measurement time of more than a factor of 2. With that, I would like to summarize. What did we learn? We learned today how to set up a measurement with a lock-in amplifier. We learned how to set up a measurement with the Boxcar Averager and how those 2 techniques work. We learned how to avoid typical pitfalls, but also how to find the best settings and therefore perform great measurements, first of all for the spectroscopy measurement and also for a pump probe-like measurement done with the Boxcar and the lock-in amplifier. And I very much hope that this saves you measurement time in the future. Thank you for your attention.
Many thanks to Claudius for this interesting and comprehensive insights. I'm sure that there will be questions from the participants regarding your explanations, which you can now answer. But first of all, I have another note to the audience. You can still ask questions by entering them below the presentation window. We already have questions, and I would like to start the discussion with the following one. Claudius, in the slide 13, the reference signal comes from the MFLI itself. Is that correct?
Thanks, Kirsten, for the first question. Yeah, that's absolutely correct. But of course, we can take the signal from very different sources, also from external sources. I will quickly jump into the Lab 1 user interface. So in a way, as you can see here, we define the reference in the lock-in amplifier, and the signal is sent out via the output amplitude. But at the same time, we can choose the reference to be external. We can there then define the certain input and lock the internal oscillator to the external signal.
Okay, perfect. Thank you for this clear answer. The next question would be, if a user uses a DAC card to capture all the data, is it possible to send out the results as an analog signal?
Thanks again. This is a really great question. I would like to share the Lab 1 user interface again. Yes, of course it's possible. I mean, this is at the key of a lock-in amplifier. Otherwise, it would be only a signal acquisition device, right? And I would like to highlight here where you can see kind of this is where we transfer the data to the computer, and now we can go to an additional auxiliary tab. The auxiliary tab can send out signals to 4 auxiliary outputs, which are actually our signal output, but we can freely address a certain signal to that. For example, in the very classical way, you can, for example, to assign to the first signal demodulator X of the first demodulator and Y of the second demodulator to the second output. Now, what we have implemented here in addition, I mean, the input of a data acquisition card is typically 0 to 10 plus minus 10 volts, and we want to use the full dynamic range. Therefore, we implemented the possibility to scale the entire signal, for example, by a factor of whatever 100, and what you will see immediately, you'll see a change in the actual value over here. Now we are in the millivolt level. Let's speed that up by 2 orders of magnitude. So now we scale by a factor of 600, and you can see the output range visualized here. So here now we go from plus minus 1 volt roughly. This has the big advantage that you can really ensure that you get all the information out to the data acquisition card or whatever other device you want to use afterwards. And you also have the possibility, for example, to limit the output to something like plus minus 10 volts, plus minus 1 volt, for example, to protect your other instrumentation. Guess we can go to the next question.
Yeah, first let me thanks for these great explanations and all, and that we have all these possibilities lock-in here. Now, the next question would be, you have showed how to modulate a laser. Now, can you output a sawtooth to tune the laser from the lock-in as well?
Yes, absolutely. Again, I would let's stay in the user interface. So it depends what the sawtooth needs to be able to do. For example, in our example of a periodically swept tunable diode laser, I would use actually the sweeper. So with the parametric sweeper, we can select, for example, the output amplitude offset, and there we can, for example, sweep the output of the amplitude starting always from, say, 0 volt up to 10 volt using our signal output and having the sawtooth on top of the modulation, so that you can control your tunable diode laser with the lock-in amplifier and modulate the signal at the same time.
Ah, okay, perfect. Now, what about the output voltage? There is another question concerning the input voltage level, and this is whether it's needed to auto-adjust this level.
That's a very good question. Of course, this is essential, right? It is of paramount importance to really have the best signal input settings, and this is not only the range. Of course, we can adapt the range, and the range should be chosen in a way that you don't clip the actual signal, but that you also use the dynamic range as good as possible. So maybe we can have a, so if we go to the different view, and we have the signal inputs here on the left-hand side. Here we have this range indicator, and as you see here, the signal at the current point in time is super tiny. So in this way, we want to minimize the range to enlarge the signal. But now this was with without any signal plugged in. Now let me plug the signal in again, and you see that we use a big portion of the dynamic range now, and we can even, depending on the signal coming in, we can this is even changed and needs to be adapted. But this is also true not only for the range itself, but also for the AC-DC coupling. So if you have let's assume you have a big DC component, this means you have a big pedestal of several volts, and your signal changes only minutely at the very top. Then you want to have, of course, not the AC, but not the DC, but an AC coupling to get rid of this DC part, which kind of saturates your input stage. In the same way, you want to adapt the impedance in the right way. So if you have a 50 ohm detector, you would like to couple with 50 ohm, otherwise more likely with 1 mega ohm, or even use a differential input, depending whatever your signal actually looks like.
Okay, thank you for this great explanation here. Now the next question is quite easy to answer, I guess. It is, what is the name of the software that you use for the simulation?
I'm not entirely sure if I got the answer correct. The question is what software we use here. We use our own Lab1 software. This software runs on the devices and can be accessed using browser windows. You type in the IP address, for example, of your device if it's connected to the network, or you have a direct USB connection. And this is our own software, and this comes with every device. Can be installed on as many instruments as you want, and at the same time you can use several different APIs like MATLAB, LabVIEW, Python, C, and .NET to control our devices on top of that and automate the measurement even more and integrate it into your measurement software.
Yeah, I think that answers the question. So the next one is about Lab1 running in the cloud. Is it mandatory to have an internet connection all the time?
Yeah, it's a perfect follow-up question. No, it's not. Lab1 runs either on the devices themselves, so there's a data server, web server running on the device itself, which we can access, or it runs on a computer which is connected to the devices, and which then provides the entire software and the user interface. So there's no internet connection needed, of course, and you can run it completely in an isolated system, as most people do in the lab.
Okay, perfect. So the next question is about the low-pass filter that was used. One user thought that the band-pass filter centered around the signal peak, but suppressing the low frequencies. Is that correct?
I'm not entirely sure if I got the question right, but let me quickly jump back to the actual slide. I think this is important. So again, the lock-in amplifier, how a lock-in amplifier works is we have the two signals, the input and the reference signal, which get mixed and then sent into really a low-pass filter. If we do so, of course, the result is what you see on the bottom. The result is an adaptive bandpass filter, which actually follows the reference. And precisely at that point, it's of course completely different from a classical bandpass filter, which you can solder together. It's really the bandpass which the lock-in actually forms, follows the modulation frequency, even if that changes, but is implemented having a low-pass filter operating at this precise frequency. And what you do, you you kick out, you filter out the reference signal, and you look only at the beat notes of the actual signal. And this is how lock-in amplifiers work. I hope this answered the question, although it wasn't maybe not entirely clear.
Well, I think so. If not, the user can ask a follow-up question, because this is still possible. You mentioned the lock-in reached the white noise floor. How can the Boxcar Averager beat that? Okay, this is an actually very good catch. I mentioned this when I talked about the SRS instrument, SRS microscopy measurement, and the actual reason is the filter characteristics. So the Boxcar and the lock-in amplifier have a slightly different settling, and although they capture basically the same amount of noise for a certain precision, so if you want to, for example, follow a step response up to 99% of the step, you need to wait a smaller amount of time with the Boxcar filter than with a lock-in amplifier, and this is where the difference actually comes from in the end, if you're in the regime of shot noise or really white noise floor. Oh, okay. I think the next one is a follow-up on that, and this is also our last question. Does it matter where the box actually is? Does it have to be exactly placed on the pulse? I would like to share maybe also one of the last slides again to explain this a little bit better. So maybe this one suits best. So yes, the box has to be located at the pulse, because what the Boxcar Averager does, it integrates over this Boxcar window, and so the main part, the major part of the signal should be contained. Now, will you measure something if you measure a little bit outside? Yeah, for sure, pretty sure, because there is still some residual signal also in this temporal section. Now, what I would always suggest is to have the Boxcar window a little bit broader, because it turns out that averaging over a little bit bigger range is not as painful as missing too much of your signal, and therefore take the Boxcar window, make it a little bit broader as the pulse which you
have, and then even if your pulse, for example, jitters in this window, this will then not affect the measurement at all.
Hey,
so I think
that is a perfect explanation to our last question. Well, Claudius, thanks a lot for the excellent presentation and for your perfect answering of all these interesting questions. I also would like to thank all participants for their interest in our webinar. Now I would like to conclude by pointing out once again that we have recorded today's webinar and it will soon be available on our website prophysik.de. You as participants will be informed by us as soon as the recording can be accessed online. Thanks again for participating in the webinar. Have a nice day, stay healthy, and see you at the next prophysik.de webinar. Bye bye.